Okay. So I'm Grant Rotskoff.
I'm Andy Mitchell.
And we're going to be talking today about an approach to solving committer problems that relies on active importance sampling, which is important when you have variational objectives that are dominated by rare events. And we're going to be discussing primarily the numerical results and aspects of that, but there are also significant consequences for optimization and generalization that you can read about in the paper. So transition path sampling is a very important problem in chemistry and physics. Characterizing transition paths is fundamentally a rare events problem as well. And there are sort of two historical perspectives on how to deal with these difficult sampling problems. One is relying primarily on spectral methods, in which you try to characterize the rate of transition through the spectrum in the existence of a gap, which is characteristic of metastability. The second approach relies more on a consideration of the paths themselves and looking at transition path theory, or sometimes potential theory, a perspective that was introduced by Bouvier, Wien and among it many others. This type of system has a sort of canonical perspective, which is relatively easy to illustrate on a one-dimensional example. So, for example, you could have state, which is specified by some domain A, and a target state, which is specified by some domain B, and you want to know about reactions between them that occur under a stochastic dynamics like that described in equation 1. So if you have an underdamped Langevin equation, or overdammed Langevin equation in this case, then this is ergodic with respect to probability density, which is characteristic of a Boltzmann distribution. And we define the committer function, the object of interest in this paper, to be a conditional probability distribution. And that conditional probability distribution simply asks, given that my dynamics starts at a particular point x outside of the domains A and B, what is the probability that the time at which I hit B is less than the first time at which I hit A? So that directly quantifies the probability of reacting. It's an object that is closely related to the notion of a reaction coordinate in chemistry, and it's one of significant interest for applications in that area. So it's relatively easy to turn this into a partial differential equation. So if we let L be the infinitesimal generator for the dynamics that we described in equation 1, this equation satisfies, so we can develop a backward Kolmogorov equation using this generator for Q itself, which is a boundary value PDE, in which the boundaries are conditioned to be 0 in A, so the probability of reaching B before A, if you're already in A, is 0, and similarly Q is 1 inside of B. So in one dimension, there's no issue here. We can solve directly for Q, given a potential V. It just requires doing quadrature in one dimension, and we can check by inspection that the solution that we get satisfies the above PDE. And so I'm just going to show a simple plot of what this looks like for a one-dimensional double well. And this is primarily just to expose the viewer to the types of plots that we're going to be showing later on, but basically all this is indicating is that in solid colors the contours of the energy landscape are plotted, and then the lines are isosurfaces of the committer. So the committer is an object, in this case in 2 dimensions, and it's although we're only solving it along the x-axis. And essentially what it's showing you is that as you reach the saddle point, the probability of reacting becomes roughly 50%. And so there's a region along which a committer isosurface along which the probability of reacting is exactly 1/2. So that illustrates that this is really telling you about the nature of reaction coordinates for the system. Of course, in practice and the types of problems that we're interested in biophysics and chemistry, this is not really a satisfactory way of approaching the problem. We can't typically solve the PDE associated with the committer because it is both a very high dimensional PDE. The coordinates that would be arguments to the committer are in extremely high dimensional spaces when we have interacting particle systems or molecular systems. And then in addition to that, there is a separate problem, which is that the data that would be necessary to actually evaluate a probability distribution for the system is quite rare relative to the typical states that would be sampled by, for example, a molecular simulation using an ergodic dynamics like the one in equation 1. So this problem that the typical time of a reaction is very long relative to the time that we can simulate is the motivation for a large body of research in molecular biophysics and computational chemistry about importance sampling. So importance sampling turns out to be key in this algorithm, but it's not always tractable in high-dimensional systems because you generally, in order to importance sample, you need to project down into a lower dimensional coordinate space. That's where the art of choosing appropriate reaction coordinates often enters the equation. In addition to this, there's a comment about why to prefer this perspective as opposed to focus on low-lying eigenvalues, which is that in this approach, we're conditioning very directly on the reaction of interest. So rather than focusing on, say, all of the transitions in the system and just identifying which of them are slow, here we're really isolating a single transition and saying this is the one that we want to focus on. So it's a problem that is maybe not as general as solving an eigenvalue problem for this type of system, but it's something that gives you a bit more direct insight. So what we're going to show you in the remainder is basically numerical results illustrating that this works and illustrating that importance sampling is a very important component of actually making this work. But in the paper, which I would encourage you to read, we also show that under very general assumptions, importance sampling asymptotically improves the generalization error. So importance sampling is crucial for this problem. We there outline in great detail an algorithm for active importance sampling, one that we'll describe in the next few slides, which enables variance reduction for an estimator of a loss function that we can utilize even in high dimensions. We also demonstrate numerically with results that we'll show you here that this algorithm performs very well in both low and high dimensional examples, and that even when the total amount of data is the same between an importance sampled version and a version not using importance sampling, the version using that does not use importance sampling will fail. Okay, so let me just briefly say what the actual objective function that we use is. So we can turn the PDE that we started with into a variational problem. And that variational problem just involves minimizing a cost functional, which is a Boltzmann-weighted average of the squared gradient. So that looks like a relatively easy object to compute. And in fact, it's something that in principle you can sample directly by doing the dynamics, the Langevin dynamics, which will asymptotically sample the Boltzmann distribution and just computing the gradient of Q along this and computing 8 to optimize a neural network. Several papers have attempted to do this. The issue with directly sampling the Boltzmann distribution, of course, is that it's metastable distribution that can be very difficult to sample when a rare event is relevant to the objective. And so, as you can see, this objective will be dominated by the rarest samples because the transition interface is relatively small. So the points at which Q is changing rapidly, so where the gradient is large, or far from zero, will be very rare under the equilibrium statistics of the system. So you need to bias in order to resolve C of Q well. So that's something that is very straightforward to illustrate on a one-dimensional example. So in this case, we're just taking, again, a double well potential, and here we can sample the probability distribution in a pretty trivial way, right? And even with quite a lot of data, so as you can see on the top right, we have a fairly good representation of the probability distribution function, although of course there's a little gap there that makes it imperfect. That poor resolution at the transition interface leads to an empirical loss function, which is quite different from the population loss function, and leads to parameters for a representation of the committer, which in this case, because it's so simple, we can just parameterize it by a single sigmoid function with two parameters that has these aberrant local minima that lead to a solution which is quite poor relative to the true minimizer, which is shown in red in comparison with the exact committer in the top left. So Andy is going to now take over and talk about how we actually do this for more complicated systems.
So the solution to this problem in more complicated systems is to use importance sampling, as has been discussed. Generally, the technique that we'll use is umbrella sampling. So this involves collecting biased samples based on the current representation of the committer. So you can see in this figure these different windows that have collected biased samples at this point all along the coordinate in the one-dimensional potential, such that we are now collecting rare data that was not sampled under the Boltzmann distribution. So we can use this umbrella sampling technique, which is well established in the statistical mechanics literature, to sample, collect data, and then use your favorite energy reweighting method to unbias the data to compute your loss function. You can use the equation that you see on the screen, or you can use a technique like the multi-state Bennett acceptance ratio, whatever floats your boat for your umbrella sampling needs here. As an illustration in 2 dimensions, still a relatively low-dimensional example, but a classic one nonetheless, we demonstrated this technique on the 2-dimensional Müller-Brown potential, trying to characterize transitions between the 2 deepest basins in this potential. On the top here, we can see the application of our technique with this importance sampling, where we collected rare data biased around transitory values of the committer function. This result coincides qualitatively with our intuition in that the committer is changing rapidly over this saddle point, with the 50% mark just about at the saddle point itself. On the right, we can see a slightly more quantitative illustration of the accuracy of this representation of the committer. What we have here is a histogram that compares the computed value of the committer function in red with the simulated probability of reactivity in blue when we initialized 100 samples from various values of the committer function and let them react. We can see pretty good agreement between the red and blue bars in this histogram. That corresponds to a fairly accurate representation of the committer. If we do not use an umbrella sampling or importance sampling technique, really the committer is only incentivized to learn to not be in either boundary. And because we don't collect any samples from this region in between the 2 potential wells, the committer will just kind of hang out in the middle and not be incentivized to learn a better representation that focuses more on the saddle point. We see this happening in this lower row. The committer characterizes the transition very poorly, both qualitatively and quantitatively. Qualitatively, it's kind of in this third sort of metastable basin. It's not characterizing the transition as happening at the saddle point at all. And then more quantitatively, in this committer analysis on the bottom right, we see that the representation of the committer is far more biased towards basin B than it is on basin A, a very poor representation of the committer in general.
and these two plots use exactly the same amount of data.
That's right.
So we also have tried this approach in higher dimensional systems. So this is one variant that we've explored, and this is an Ising-like model, which has Dirichlet boundary conditions to create metastability. So you can view this as a system of coupled spins that either prefer to be up or down, and those coupled spins are evolving according to the SPDE in equation 15. So in this case, there are these two metastable states, but here a reaction coordinate maybe is less obvious for the pathway, and the committer in this case is a 144 dimensional function. So that mapping is one that's complicated to parameterize. But nevertheless, the algorithm that we use seems to achieve good results. So you can see that by looking at the evolution of the loss function, so an average of the gradient of Q over the sampling. And you can also see it in the transition pathways, which illustrate a kind of characteristic hourglass shape. And so this is something that is indicative of correctly characterizing the committer, because at the central points you have essentially a 50% chance of either nucleating the blue domain or nucleating the red domain. And this system has been studied and characterized in other using other approaches, so it's something that we sort of know the answer to. So with that, I would encourage you to go and read our paper for a bit more detail about the algorithm and for more of the analysis, which is sort of the heart and meat of the paper. So thank you for your time, and look forward to